Hey, and welcome to my video on the basics of solving linear recurrence relations. Before we begin, I'll just give a quick disclaimer about the prereqs. I try to make my videos as accessible as possible, but sometimes some prior knowledge is important to understand the concepts we talk about. All of the mathematics here is understandable with some basic knowledge about linear algebra, such as matrices, determinants, and linear independence, but it's also fairly useful if you know how to solve linear differential equations, since the strategies there are about the same as the ones here. As such, I recommend understanding the basics of discrete calculus, which was the topic of my last video, the basics of linear algebra, and the basics of solving linear differential equations. With that out of the way, let's get to it. To start, let's look at the sequence we saw at the beginning of the last video, written slightly differently in the form of a recurrence relation, also known as a difference equation. I should note that the values of the sequence which are not defined recursively are called initial conditions. In this case, the initial condition is a of 0 is equal to 1. Some of you may have seen a sequence like this before, and so some of you might know the closed form expression for it, which from now on we'll call the solution to the recurrence relation. Regardless, let's explore how we might come up with the solution on our own. The first thing to note is that our solution will be unique for natural numbers n. This is clear because every value of our sequence is uniquely determined by our definition. We can always calculate a of n in exactly n simple integer multiplications. We can find that a of 0 is equal to 1 just from the definition, a of 1 is equal to 2 times a of 0, which is 2 times 1, which is 2. A of 2 is equal to 2 times a of 1, which is 2 times 2, which is 4. A of 3 is equal to 2 times a of 2, which is 2 times 4, which is 8. And a of 4 is equal to 2 times a of 3, which is 2 times 8, which is 16. By shifting the index of our definition, we get the following. A of n plus 1 is equal to 2 times a of n. We can compose this k times to get a formula for adding inputs. A of n plus k is equal to 2 to the k times a of n, which you could prove by induction if you really wanted to. From this formula, we can actually come up with a closed form expression for the sequence. First, we'll set n equal to 0, and then a simple change of variable. And now from our definition, a of 0 is equal to 1, and so a of n is simply equal to 2 to the n. This makes sense, as adding 1 to the input translating to the output being multiplied by 2 essentially defines 2 to the n, and 2 to the n is of course 1 at 0. If we weren't given the initial condition of a of 0 is equal to 1, we would be forced to write the solution as a of n is equal to 2 to the n times a of 0, which is called the general solution to the recurrence relation since it applies regardless of initial conditions. Now, because our sequence is only defined for natural number inputs, we can of course add an expression that is 0 for all natural numbers n, such as sine of pi n, or 1 minus negative 1 to the 2n to our solution, or we can multiply our solution by a function which is 1 for natural numbers n, such as cosine of 2 pi n, or e to the sine pi n. If you only care about natural numbers, this still means that 2 to the n is a unique solution, since none of those transformations produce different values. So for this sequence, we know that a of n is equal to 2 to the n times a of 0 is a unique closed form solution. Let's look at a different recurrence relation that shares some of the same properties. Just like with the previous recurrence, we can uniquely determine all the values of a of n. So a of 2 is equal to a of 1 plus 2 times a of 0, which is 2 plus 2 times 1, which is 3. A of 3 is equal to a of 2 plus 2 times a of 1, which is 3 plus 2 times 1, which is 5. And a of 4 is equal to a of 3 plus 2 times a of 2, which is 5 plus 2 times 3, which is 11. One important difference between this recurrence and the last one is that we now have an a of n plus 2 as well as a second initial condition. This is what we call a second order recurrence relation because the greatest difference between the inputs in the relation is 2. In a kth order recurrence relation, the greatest difference between the inputs in the relation is k. In general, a kth order recurrence relation will have a unique solution on its domain given k consecutive initial values. Another important similarity between this recurrence and the first one is that they are both linear recurrence relations. A kth order linear recurrence can be written in the following form for some sequence of functions p sub I of n and some function g of n. These are called linear because the recurrence relation is defined by a linear combination of earlier terms in the sequence. A recurrence relation is additionally considered homogeneous when g of n is equal to 0, which is true for both of the recurrence relations we have talked about so far. Homogeneous linear recurrence relations have the useful property that ignoring initial conditions, linear combinations of solutions will still satisfy the recurrence. To prove this, let's suppose we have two solutions x of n and y of n that satisfy a linear homogeneous recurrence relation and two arbitrary constants c1 and c2. We will then show that a of n is equal to c1 times x of n plus c2 times y of n also satisfies the same recurrence. In writing, we have this. So we're going to prove that a of n satisfies the same recurrence relation. So we're going to go ahead and shift the first line by k. Then we're going to plug in our expressions for x of n plus k and y of n plus k, distributing the constants. Then we can pull out the p1 of n and p2 of n and pk of n. And now these sums are simply the definition of our sequence A. And so therefore A satisfies the same recurrence relation. This property ends up being extremely useful in solving such recurrence relations. Just like from earlier, with the recurrence relation alone and no initial conditions, we are able to create a general solution for the recurrence relation. The general solution to a recurrence relation must have enough unknowns to satisfy every set of initial conditions while always satisfying the recurrence relation. Because evaluating a kth order linear homogeneous relation depends on k initial conditions, the general form for a kth order recurrence relation will have k unknowns and k degrees of freedom. This is so that our k degrees of freedom subtracted from the number of constraints we need to reach uniqueness, which is k from the initial conditions, is 0. If we have one solution, a1 of n, to a kth order homogeneous linear recurrence relation, and we multiply it by an unknown constant c1, we will have 1 degree of freedom through that constant. If we take another solution to the same homogeneous linear recurrence relation, a2 of n, and we multiply it by another unknown constant c2, then we will also have 1 degree of freedom. If we add these two expressions together, they will remain solutions as shown, and they will maintain each of their degrees of freedom when the two solutions are called linearly independent. In fact, if we had k solutions each multiplied by one of k arbitrary constants, their sum would have k degrees of freedom when all k solutions are linearly independent. This set of k solutions is called the fundamental set of solutions for the recurrence relation, since a linear combination of the elements of the set can uniquely solve the recurrence relation for any k consecutive initial values. As a result, it's pretty useful to know whether or not sequences are linearly independent. A sequence of k sequences, ai of n, is linearly independent if and only if a sequence of zeros is the only sequence of constants ci, such that a linear combination of the sequences using those constants is 0. This definition on its own is fairly hard to use, but we can create a more usable form with a bit of manipulation. From the definition, we can generate another k-1 equations by shifting the index of our sequence. Then, we can use a matrix to rewrite this as a system of equations. Linear algebra tells us that this equation will exclusively have the trivial solution, where all the ci are 0, if and only if the determinant of our matrix is non-zero. This means that if the determinant of our matrix, which is called the Casarati matrix after the Italian mathematician Felice Casarati, is not identically 0 for values of n in the domain of our sequence, the elements in our set of sequences, ai of n, are linearly independent. This determinant is called the Casaration of our solutions. This is the discrete analog of the Wronskian. In fact, some authors use w of n instead of c of n to denote the Casaration for this reason. Remember that if the Casaration is non-zero for any value of n in the domain of our sequence, our solutions are linearly independent. Also note that we only care about the values of the Casaration at values of n in our domain. Otherwise, we would be able to conclude that sine of pi n is a part of a fundamental set of solutions, which it certainly is not for any natural number indexed sequence. Let's look back at our specific recurrence. A of n plus 2 is equal to a of n plus 1 plus 2 times a of n. Now that we've talked a little bit about the theory of linear recurrence relations, I'll show you how to solve this particular recurrence relation. The process is going to seem a bit mystical, but just go with me. In a future pair of videos, I'll go way too in-depth into the origin of these solutions. Let's first solve a recurrence relation for 0. Because this is a second-order homogeneous linear recurrence relation, to find the general solution, we need two linearly independent solutions, and the general solution will be a linear combination of these two solutions. It turns out that if we create what's called the characteristic polynomial for this relation, the roots of the polynomial raised to the nth power will solve the recurrence relation. The characteristic polynomial for a kth order linear homogeneous recurrence relation with constant coefficients is the polynomial of r, where the term in front of r to the k is the term in front of a to the n plus k. This is extremely similar to solving homogeneous linear differential equations with constant coefficients. We can now write the characteristic polynomial for our sequence, then solve for its roots. So we get r squared minus r minus 2. So this will factor out into r plus 1 and r minus 2. So r is then equal to minus 1 or 2. We can raise these roots to the nth power to get the two solutions to our recurrence relation. We can verify that these are solutions by plugging them back into our recurrence relation. So we'll plug in our particular sequences. And then on the top line, we're going to factor out a minus 1 from the first term, and on the bottom line, we're going to combine the 2 into the 2 to the n. Now we're going to combine like terms. And now we're going to rewrite the 1 as minus 1 squared. And then on both lines, we're going to add exponents. So since the left-hand side is equal to the right-hand side, our two particular solutions do indeed follow the recurrence relation. So now that we have two solutions to our recurrence relation, in order to conclude that our general solution is a linear combination of these two solutions, we need to prove that our solutions are linearly independent. We can check this by finding a point where the cancellation of our solution is non-zero. So we can plug in 0 into the cancellation, and then substitute in our particular functions. Now the top line becomes 1, and the bottom line becomes -1 and 2. Then we can apply the definition of a 2 by 2 determinant. Multiplying, this becomes 2 plus 1, which is of course 3, which is of course not 0. This means our solutions are linearly independent. In fact, we can show that all exponential sequences are linearly independent without too much effort. For a set of sequences r sub I to the n, the cancellation at 0 becomes this, which those of you who have taken a linear algebra course should recognize as the van der Waals determinant of the roots, which is equal to the product of their differences. So this, which by the zero product property is never 0 if the roots are distinct. This means that distinct roots of a characteristic polynomial are always linearly independent. If you haven't seen a van der Waals determinant before, I've linked the Wikipedia page for the van der Waals matrix as well as the proof wiki page for this formula in the description. So the general solution to a of n plus 2 is equal to a of n plus 1 plus 2 times a of n is then c1 times a1 of n plus c2 times a2 of n, which is c1 times -1 to the n plus c2 times 2 to the n. This solves our recurrence relation and has 2 degrees of freedom to match the number of initial conditions we need. Now we need to bring back in the initial conditions. First, we'll plug in n equals 0 and 1 into our general solution. Then we can recall that our initial conditions were 1 and 1. So this top line becomes c1 plus c2, and the bottom line becomes minus c1 plus 2c2. Then we can add the first line to the second line, and then add like terms, and we get that 3c2 is equal to 2. So we can divide out that 3, and we get that c2 is equal to 2/3. We can subtract the second line from the first line, and then again subtract, and we end up with c1 is equal to 1/3. This means that the specific solution for these particular initial conditions is a of n is equal to 1/3 times -1 to the n plus 2/3 times 2 to the n. If we plug back in values for n, we get the exact same values that we calculated at the beginning. So a of 2 is equal to 1/3 times -1 squared plus 2/3 times 2 squared, which is 1/3 plus 8/3, which is 3. A of 3 is equal to 1/3 times -1 cubed plus 2/3 times 2 cubed, which is -1/3, plus 16/3, which is of course 5. And a of 4 is equal to 1/3 times -1 to the fourth, plus 2/3 times 2 to the fourth, which is 1/3 plus 32/3, which is 11. Note that if we had picked different initial conditions, we would get different constants. For example, let's try a of 0 is equal to 1 and a of 1 is equal to 2. So again, we'll look back at our general solution evaluated at 0 and 1, and then we'll plug in these initial conditions. Again, the top row becomes c1 plus c2, and the bottom row becomes minus c1 plus c2. Then we'll add the first row to the second row, then combine like terms, and we get that 3 is equal to 3 times c2. So dividing by 3, c2 is equal to 1. Then we subtract the second row from the first row, and simplify, and we get that c1 is equal to 0. So therefore, with these initial conditions, our solution is a of n is equal to simply 2 to the n. This is the exact same solution we saw from the very beginning of the video with a different recurrence relation. That's right, a single sequence can be defined by many different recurrence relations, some of which can be much more complicated than others. Let's try a different problem. S of n is equal to the sum from k equals 0 to n of k. Many of you will have seen this before and will know the solution, but solving this problem as a recurrence relation will reveal two interesting scenarios while providing a new proof for a well-known formula. First, let's turn this into a recurrence relation by taking the forward difference of both sides. So everything except this top term is going to cancel out, and we end up with delta S of n is equal to n plus 1. If we use this as a recurrence relation now, we won't be able to solve it with our current toolset because the relation won't be homogeneous. There's that pesky n plus 1 term, which isn't 0. There's a trick, though, referred to as symbolic differentiation. If we just keep taking the forward difference, eventually the recurrence relation will become homogeneous. So the second forward difference becomes this, and everything cancels out except that one in the middle, and then the third forward difference becomes 0. Sweet, now we can create a homogeneous recurrence relation. It turns out in the general case, an nth order polynomial can be reduced to 0 with n plus 1 iterations of symbolic differentiation. This can be shown using induction by taking advantage of the linearity of the finite difference operator. We've already seen that a first order polynomial takes 2 steps, and we can show that the finite difference of x to the n in respect to x decreases its order by 1. So delta of x to the n is this, and we can rewrite the first term with the binomial theorem. And now the very last term of the sum, k is equal to n, will be n choose n of x to the n, which is just x to the n. So subtracting out that x to the n at the end there, the last term disappears, and we get the sum from k equals 0 to n minus 1 of n choose k times x to the k. This is an n minus 1th order polynomial, so since our order got reduced by 1, this is enough to show that an nth order polynomial can be reduced to 0 with n plus 1 steps. Note that the order of our recurrence will go up by 1 each time we differentiate in this way. So let's expand out the definition of the forward difference operator until we have a proper recurrence relation. So we can rewrite the third difference in terms of the second difference, and we can write the second difference in terms of the first difference, and then we're going to have 2 of the term in the middle and 1 of the term in the end. Then we can write the first difference in terms of the sequence itself. And now we're going to have 3 of each of the terms in the middle and 1 of each of the terms on the end, which is suspiciously similar to the binomial coefficients. At this point, we have a third-order homogeneous linear recurrence relation. As such, we need 3 independent solutions to come up with the general solution of the recurrence relation. To do so, we can write the characteristic polynomial and solve for its roots. So r cubed minus 3r squared plus 3r minus 1 is equal to 0, and so this factors out into r minus 1 cubed, so r is of course 1 or 1 or 1. If you couldn't tell, this is somewhat of a problem. We won't have 3 distinct solutions to form our fundamental set just by using the roots, but don't worry. Just like repeated roots in differential equations, where we just multiply our solution by x to the k, where k depends on how many times the root is repeated, we multiply our solutions s of n is equal to 1 to the n by n and n squared. So these are our 3 solutions. And of course, the 1 to the n doesn't contribute anything, so our solutions become 1, n, and n squared. So first, let's confirm that these are actually solutions. So we're going to write the recurrence as a sequence r, and then show that the sequence is uniformly 0. So first, we'll plug in our particular solutions of 1, n, and n squared. And then we're going to go ahead and expand out these quadratics in the bottom. And now on every line, we're going to distribute. And then we're going to reorder the terms so that cancellation becomes obvious. So all of these terms are going to cancel out, and therefore the recurrences all become 0, and thus these 3 solutions do indeed satisfy the recurrence relation. Now we need to show that these solutions are independent. So the cancellation becomes this, and we can plug in our specific sequences of 1, n, and n squared. And now we can plug in n equals 0. And so all the frills are just going to disappear except the bottom term, which is going to become 4. Then we can apply the definition of a 3 by 3 determinant. And then only the first determinant matters here because of the zeros and the ones. And that determinant becomes 4 minus 2, which is of course 2, which is not 0. So our solutions are independent. We're now able to write the general form for our recurrence relation. S of n is equal to c1 plus c2n plus c3n squared. All that's left is to plug in the initial conditions. We weren't given any initial conditions, but we can actually figure them out from the problem we were originally trying to solve. So we'll plug in 0, 1, and 2 into these sums. And now these, of course, become 0, 0 plus 1, and 0 plus 1 plus 2, which is, of course, 0, 1, and 3. So we'll just flip this around to make it easier. And then we'll go ahead and plug in the general solution for these evaluations. So now the first line will just become C1, the second line will become C1 plus C2 plus C3, and the third line will become C1 plus 2C2 plus 4C3. So we can just go ahead and subtract the first line from the second and third line just to get rid of that C1 term. Then we'll subtract 2 times the second line from the third line, and after simplifying, we'll get that 1 is equal to 2 times C3. So divide by 2, C3 is equal to a half. Then we can subtract the third line from the second line, and then simplify again, and we get that C2 is also equal to a half. So the solution becomes S of n is equal to 1/2 n plus 1/2 n squared. We can write it into a more common form of n times n plus 1 all over 2. This is the nth triangle number, which is the formula generally given to students for the sum of the first n natural numbers, which is exactly what we were solving for. Putting this next to the original definition of our sequence, we can see that it corresponds perfectly. Many of you probably already knew this formula, but this is a cool new way of deriving it without induction, and I think that's pretty neat. Well, I think that's enough for this video. Oh, actually, one last thing. I feel obligated to cover what happens when you have complex roots of the characteristic polynomial. I personally am fine leaving the roots in the form 3 plus 2i all to the n or whatever, but if you have complex number phobia like some people do, A, you should get over that, and B, I'll give you a neat exercise to help you get over that. The complex roots will come in conjugate pairs. Rewrite each of the complex r to the n using the polar form of r and Euler's formula to create an equivalent expression for r to the n that involves the sine and cosine functions. If you get stuck and need some help, just drop a comment and I'll do my best to respond. Well, that's all I've got. Thanks for watching, and I'll catch you in the next one.